In this lesson, we'll look at area for curves that cross the x-axis and also area between curves. But to start with, I'd like to do just a quick review of integrating or antiderivatives and indefinite, indefinite, and just to refresh our mind on the kinds of things we've been covering in the last few lessons, because it can start to add up and a quick review can help settle it in your mind. So this right here, you can see there are several things we're integrating, and we can do them separately. So I'll integrate x to the third. Remember, we're going to use a power rule, n plus 1 over n plus 1, x to the n plus 1. In this case, n is 3, so we have 1 over 3 plus 1, 4, x to the 3 plus 1 fourth, plus, and then we do the second one, and there's a constant there, so we'll just write down the constant, times, and then x to the fifth, so that's a power rule, so 1 over 6, x to the 6, that's the n plus 1 thing again. And then there's a minus, and then the last one is x to the minus 2, so we'll do 1 over minus 2 plus 1, x to the minus 2 plus 1. In this case, n was minus 2. In this case, n was 5. In this case, n was 3. So, and just putting those together, we have, let's just write that as x to the fourth over 4 plus, looks like x to the sixth over 4 times 6, 24. And then minus 1 over minus 1, x to the minus 1. So that's going to be x to the fourth over 4 plus x to the sixth over 24. Minus times minus is plus x to the minus 1. Well, let's just write x to the minus 1. Or 1 over x, if you like to write it that way. And then plus a constant. We add that constant at the end so we don't have to deal with it through all the intermediate steps. And here's another one. Again, we have how many terms? 1, 2, 3. Things are separated by plus and minus in there. So we'll do them each separately. So the first one, we have 12. And then n in this case is 7, 6. So it's 1 over 7, 6 plus 1. X to the 7 sixths plus 1. This is not the most fun one. And then we have a 4 times, and it's 3 fifths. So 1 over 3 fifths plus 1. X to the 3 fifths plus 1. And then plus and then it's x to the minus 4 thirds. So 1 over minus 4 thirds plus 1, x to the minus 4 thirds plus 1. And then let's try that. So we get, and plus a constant, but we'll wait, hold on to that. So 7, 6 plus 1 is 7, 6 plus 6, 6, so 13, 6. So we have 1 over 13, 6, x to the 13, 6. And then we have 4 times, and then 3 fifths plus 1 is 3 fifths plus 5 fifths, or 8 fifths. So we'll have 1 over 8 fifths, x to the 8 fifths. And then plus, and minus 4 thirds plus 1 is minus 4 plus 3 over 3. So minus 1 third. So 1 over minus 1 third, x to the minus 1 third. And let's rewrite that out. So 12 times 1 over 13, 6 is 12 times the reciprocal, 6 thirteenths, x to the 13 sixths. And plus 4 times, this is a reciprocal of 8 fifths, so 5 eighths, x to the 8 fifths. And then that's a minus, right? Plus times a minus. Reciprocal of 1 third is 3 over 1, or 3, x to the minus 1 third. And plus a constant. And there might be a little bit of simplification we can do with those fractions, like the 4 goes into the 8, so you have 5 halves, but that's pretty much it. There's no reason to try to put it all into one big expression. Now this one, this looks a little different than that. This isn't just a straight power, this is substitution, and you can see they have something raised to a power, so that's the natural place where we have u equals 2x plus 3, and we'll need du, which is, take the derivative of this, is just 2, and then there'll be a dx there. And we're kind of lucky here, you can see there's a 2 dx, so that's du right there. So we have integral of 2x plus 3 is u cubed, right? 2x plus 3 cubed, and then there's du, so we just put the du. And now we can do the power rule on that, u to the fourth over 4. Now let's unsubstitute, 2x plus 3 to the fourth over 4, and then add that constant on now. And here's one's very similar to the last one. Again, we'll make u equal to 2x plus 3, which makes du equal to 2 dx, just like before. But you can see there's no 2 in there. So we'll need to replace dx with something. So we solve this guy for dx. Dx is 1/2 du, right? Divide both sides by 2. So this guy becomes the integral of u cubed times 1/2 du. And now we'll just pull that 1/2 out. So we have 1/2, and then the power rule for antiderivatives, u to the 4th over 4, which is, let's unsubstitute that guy, 2x plus 3 to the 4th over 8, plus constant. And here's another one for substitution that's nice. So you can see the thing you kind of want u to be is the 2x minus 1 there. So we'll have du, again, is 2 dx. Oh, du is 2 dx. So if I can scroll down, no. So let's go ahead and substitute. We have the integral of 5 over u squared. And then instead of dx, we need to solve for dx here. So dx is 1/2 du. We'll just put 1/2 du where the dx was, times 1/2 du. So now we'll pull the 5 and the 2 out. So we have 5 over 2, integral of 1 over u squared du. Now let's just rewrite that as a power, 5 over 2 integral of u to the minus 2 du. And now you can see we can use the power rule. So it's 5/2 times n plus 1, u to the n plus 1, where n is minus 2. And so that's going to be 5/2 times 1 over minus 1, u to the minus 1, which is minus 5/2 u to the minus 1. Now let's go ahead and put that, unsubstitute it. And so it's 2x minus 1 to the minus 1. It's pretty good like that. Or, I mean, you can, if you really want to break it up, you can give 4x minus 2. You could do it like that. But I liked this one right here. Okay, now here's one where we use, you can see we have a monomial. So we'll break that up into 3, 4x cubed over x squared, minus x squared over x squared, plus 2 over x squared dx. And we'll break that into, so we have 4x minus 1 plus 2x to the minus 2. I'm going to save a little time and just say, well, let's do each of these separately. So 3. So we have 4 times, integrate this guy, we get 1/2 x to the squared, minus, and then 1, any constant, you just throw an x in, minus 1x, plus, and then we have 2 times, and then in this case is minus 2, so we'll just be careful and do the power rule explicitly, and then plus a constant, but let's hang on to that. So 4 times 1/2 is 2x squared, minus x, and then that's 2 times minus 1, so minus 2x to the minus 1. It's pretty good like that. And then the last step, plus c. So if you accidentally draw the box and you're like, oh, plus c, just write a plus c on the end there. All right, so use the fundamental theorem of calculus. Now this is this little gem. The fundamental theorem says if you have a definite integral from a to b of a function with a little f, then you can solve that guy by using the antiderivative, evaluate it at b and evaluate it at a, and subtract the two. So let's see, do we have an a and a b and a little f? You say, oh yeah, it's from 1 to 2. So from 1 to 2, the little f is 1 over x. So 1 over x. And when you integrate 1 over x, that's a special one, we know that we get natural log of x with little absolute value bars. So this guy, by the fundamental theorem of calculus, is the big F of b minus the big F of a, which is the big F of 2 minus the big F of 1. So natural log of 2 minus, oh, so that's the value, minus natural log of 1. And those are already positive numbers, so we'll just write natural log of 2 minus natural log of 1, which you could do on a calculator. But I'm just going to leave it like that. And the same thing here. Can we look at this guy? So from a to b and a little f of x. Then we'll need a big F of x. So from 1 to 2, and The little f of x is the x to the fourth. So integrate that guy using the power rule. It's x to the fifth over 5. So this guy, by the fundamental theorem of calculus, will be big F of 2 minus big F of 1. So big F of 2 is put the 2 in for x, 2 to the fifth over 5, and 1 to the fifth over 5. So let's go ahead. 2 to the fifth is 2, 4, 8, 16, 32. 32 over 5 minus 1 to the fifth power is just 1. So we have 31 fifths, or 6.2. And then this last guy here, we have 3x. So our a is, and our b, 0 to 5, and our little f of x is 3x, which makes our big F of x a little more complicated. So 3 times 1 half x squared. All right. So now we know that this is going to be f of 5 minus big F of 0. So plug the 5 in, we have 3 halves times 5 squared. And then subtract, plug the 0 in, we have 3 halves times 0 squared. So it's always nice to start with 0, isn't it? So that's just 0. And this is 25 times 3, or 75 over 5, which is 15. Pretty sweet, right? Okay, so let's move on a little bit after that review. Our fundamental theorem of calculus finds the area under a curve. And more specifically, when I say under the curve, I mean between the curve and the x-axis. So look at this picture here. You've got the x-axis and the y-axis. And it finds the area between the curve from A to B on the x-axis. And that's what this means. And we say, oh, we can do this. That's the fundamental theorem. But what if you have something like this, where you have the curve crosses the x-axis? You know, algebra, we spend a lot of time looking for roots or zeros, and that's the rational root theorem, and the fundamental theorem of algebra. We look at all those things, like what is a factor. So the reason is because things like this get complicated later on. So we want to know, because this is going to be positive area. Let's say that's 2. And let's say this is also area size 2. Then if you integrate from A to B, it'll take some negative areas and add them to some positive areas and end up with, in this case, 0. So what would we do with that? Well, let me just come back and have a mention on this. What we do with this is we say, well, where that cross is, let's call that R. You'd say, look, we need to take the area from A to R, and we need to take the area from R to B of that little f of x. And you really should never have a negative area. So that's a negative area. We make that a negative, and we add 2 at that area. So what you do is you make it 2 integrals if it crosses the x-axis. One for the negative area, and then you, on purpose, make that negative. And then, like, negative, negative is positive. And then the other one for the positive area, which you just leave as a standard. So you'd have a f of r minus f of a. You'd calculate that for this first one, and that would be a minus. And then on the second one, you'd have an f of b minus f of r. And you'd have that positive. So you can kind of see here that you're going to have a minus f of r and another minus f of r. So you'll subtract this f of r twice in this case. And that's, the thing is, often, you know, you'll just have f of x you won't necessarily know, but you have to be kind of aware that it could cross someplace and someplace, so you might need to break it up into chunks. And we're not going to get crazy with this, but here's a nice step function we use to model a lot of things in life. So if you have a function, and this is f of x, you can see it's minus 1 from 0 to 2. So if you're writing that as a Frankenstein, you'd say it's minus 1 when x is from 0 to 2, and it's 1 from 2 to 4. That's a way to write that function, and maybe make it equal to 0 and equal to 2 there. And this guy is not going to be continuous here. Obviously, we're hopping at that point. But we can still find the area, because the width of that line where it hops is 0. We just need to be careful at 2. So instead of trying to find this, which if you did, you'd say, oh, it's going to be 0, because we have a negative and a positive, we would just break it into two things. So we'll have minus 0 to 2, and then 2 to 4, just like that last problem. And that will work fine. And also area between two curves. If you kind of look here, you could say, look, the height of, if I draw a rectangle here, you could say there's the height of F is that whole length, and the height of G is this little length here. So F goes that whole distance, and G is just this little bit. So if you want to know the difference, you take F and you subtract off the G. And in general, if you're finding the area between two, you take the function F, which is all the heights here, you subtract off all the heights G individually. So we would just have the integral from A to B of the area of F minus the area of G. Or in other words, we're taking the area here of F, and then here's G a little bit lower, taking all that area, which is less. And when you subtract this off, you're left with the difference. So this is another way to write that is A to B of F minus the integral A to B of G. And this is, we're just going to assume that they don't cross the x-axis in this case also. So let's try one. Find the area between f of x equals 3x squared and g of x is 2x minus 1 on 1 to 10. So we'll go ahead and say, all right, so from 1 to 10, we have 2x minus 1, which looks kind of like this. That's 2x minus 1. And we have 3x squared, which looks something like this. And so we're interested in the area between the two. This is 3x squared. And so we'll take the area under 3x squared and subtract off this little piece of area down here. So we'll take the integral from 1 to 10 of f minus g dx. And we say, all right, integral 1 to 10 of f is 3x squared. And then minus, and g is 2x minus 1. So we want the additive inverse of g. So we want minus 2x plus 1. So I put the little parentheses there, dx. So we have integral 1 to 10 of 3x squared minus 2x plus 1. Now, we know that f of x is, we know a is 1 and b is 10. F of x is 3x squared minus 2x plus 1. What is the antiderivative of that, the big F? That's a little more fun, right? 3 times, and then n is 2, so x cubed over 3. And then minus 2 times 1 over x, or 1 half x squared, and then plus an x. So we have x cubed minus x squared plus x. That's big F of x. So if we want big F of b minus big F of a, we plug in the b, which is 10. So we have 10 cubed minus 10 squared plus 10. That's f of b right there. And then we'll subtract evaluated at a, which is 1 cubed minus 1 squared plus 1. So we have 1,000 minus 100 plus 10. So that's 900 plus 10, 910. Minus 1 is 0, so just 1. So 909 in this case. Pretty good size area. And then this last one here, if we want to find between 1 to 10 of these two guys, so x squared d to the x, x squared looks something like, so let's say 1 to 10. X squared looks kind of like this, and e to the x looks sort of like super high. And we want the area between, so we'll just take from 1 to 10, f minus g. We're just going to assume that it's always higher than g. If it crosses, you're going to have to be careful again. But we're going to make easy cases here for us because we're kind of looking for producers and consumers surplus in the next lesson. That's where we're going with this. We won't have to worry. So e to the x minus x squared dx. So f of x, in this case, little f, is e to the x minus x squared. And the big F of x, the antiderivative of that guy, is the antiderivative of e to the x, is e to the x, and the antiderivative of x squared, which is 1/3 x cubed. So if I want f of b minus f of a, in this case, here's my big F. I just take, let's see here, f of b would be 10, so e to the 10th minus 1/3 10 cubed times 10 cubed, and then minus e to the first minus 1/3 times e to the first. I'm sorry, 10 to the first. 1/3 times, let's do 10 to the first over 3. That's right, 10 cubed. All right, one more try here. E to the first minus 1/3, and then for x we plug in 1, and then we cube it. There we go. So that's not going to be pretty. That's going to be a rather large number. Let's see how big e to the 10th is. 10th. 22,000. And then we'll subtract off 1,000 divided by 3. So we have something like 21,693.13 minus, and then if you do the e to the first, minus 1/3, you get minus 10 points, so plus. Think about that. So 2 point. Oh, I hit the wrong one. Try that again. So we have e 2.7. So then here we have 2.72 minus 1/3. Let's make it that easy. So it's roughly, it's not very big. And make that a minus. And add it to 21,693. So about 21,690.7, roughly. So it's going to be a large number. And I don't want to do so much. This space should have been for the last problem, but here again you'll have the area between two curves. So immediately you should think of this. And then just start plugging in A and B. There's your A and B right there. 2 to 5. And then f is x squared plus 1. That's f. The g is x squared. That should be right. Dx. And so what do we have? We have the integral 2 to 5 of x squared. Oh, that's minus x squared. So we just have 1. So f of x is 1. And if you integrate 1, you just get x. We don't worry about constants with definite integrals. So we have big F of 5 minus big F of 2 by the fundamental theorem, which is f of 5. If f of x is x, then f of 5, this is so easy it's hard, is 5. And then f of 2 is just going to be 2. So we have 5 minus 2. How lucky, right? That kind of makes sense. If you think about it, you've got x squared. And we have x squared plus 1, which is just that guy shifted 1. And we're going from 2 to 5. So we're going 3 wide. And this guy's exactly 1 high. It's kind of like you took this 3 by 1 and you sort of bent it up. It's still got the same area, but you bent it up, and so it's still, that's kind of what happened there. Anyway, so 3 is the area there. And that's the end of the lesson.